Of Yair's talks on the geometry and topology of Teichmüller spaces.
Thank you. Okay, so where were we? I should thank everyone for coming back in spite of the first 2 hours. So we defined the Teichmüller space. We talked about this compactification. So that we take the Teichmüller space, union the projective measured foliation space. This is a cell, this is a sphere, and together they are a ball of the appropriate dimension. And then we talked about the mapping class group action on this by homeomorphisms. And then I started talking about the metric that I wanted to discuss, and so let me quickly come back to that, because that will kind of inform the rest of what I want to talk about. So the Teichmüller metric, let me say it a little more correctly. So again, you have, so if X is a point in the Teichmüller space, you should think of that as S, the surface S that we started with, equipped with, for the moment, a complex structure. So think of that as and then if you have two such points, then you can ask what their difference is, their distance in this sense, and it's the following. So it was the following thing. You consider a map, F, and I'm going to write from X to Y, but really it's from the underlying surface S to itself, and so I want to choose F to be isotopic to the identity, and it's supposed to be a way of trying to convert one structure to the other, and so we measure its failure to do that, first point-wise, so if P is in S, we look at dF from the tangent space of S to itself. But let me write it as tangent space of X to the tangent space of the image. And you can ask what it does to the, I don't want to write the formula down, but it takes a circle to an ellipse, and the ratio of major to minor axes of the ellipse. So the point is, the difference between circle and ellipse is well defined. Given a complex structure, you know what this ratio is for the ellipse. Not what the size is, but what the aspect ratio is. So the aspect ratio we'll call K F of P. And the inequality that I incorrectly wrote last time, Steve pointed out to me afterwards, is that I wrote it as an equality, but it says if you have, say, 2 points, 2 maps, you have sort of F, X to Y, and G to some Z, all structured on the same surface, then K of G composed with F at point P is less than or equal to K, I guess, of G and F of P times K F of P. And so when you take the logarithms, you'll get the triangle inequality, and so that's what we do. But we should, okay, but now we should kind of take a supremum and so on. So we now define K of F to be the supremum over all points in the surface of the dilatation. This is called the quasi-conformal dilatation. And then we let K of xy be the infimum over all F isotopic identity of K of F. Sorry, yeah, K of F. And finally, the distance, the Teichmüller distance between X and Y I guess there's a half for normalization reasons, and you write that. So that is a metric because of this inequality. Let's see. There are various things to prove. So for example, you need to prove that if the distance is 0, then X and Y are equivalent. And that is not quite as obvious as it sounds. Obviously, if you could make a map in which k was pointwise 1, then it would be a conformal map and x would equal y. But you might worry that there's some sequence of f's which have k arbitrarily close to 1, but not conformal f. So there's some kind of actual analysis that goes in here, which I'm going to duck away from. But let me just say that, so I pretended this whole time that f was a smooth map. And that gives a correct definition, but it's not the right category of maps to consider because of exactly this problem, that if you take a sequence of maps that minimize this dilatation, there's no reason to expect the limit map to exist and be smooth. I mean, sorry, so well, a priori, you don't know what's going to happen. In fact, you can find a map which optimizes this k, but not in this smooth category. You have to allow the maps to be perhaps non-smooth, and so the right category is what are called quasi-conformal maps, which I'm not going to discuss. So I'll put it in brackets, but kind of the idea here is that you actually have some kind of, you need some notion of weak differentiability. You have to do everything in this kind of weak sense of weak derivatives and so on. And there you have nice equicontinuity properties for families of maps, and you can extract limits. And so what will happen when you do that is that you will be able to understand what the extremal, the optimal maps are. And so let me just say the answer: the extremal maps, in other words, the ones that actually give the best k, are what are called Teichmüller maps. It's getting a little, everything gets called Teichmüller, so it doesn't seem to distinguish things, but later we'll have a different method. And let me say what they look like, because that's kind of important. So how do I define a Teichmüller map? Well, I have to have the right, the right coordinate in order to view it. So there's a coordinate. What do I mean? I mean, there are complex coordinates. It's going to look familiar in a second. On the surface minus, well, let's write it in fact on x, minus a finite set. So they're like charts from, say, into C. And now the transitions are going to be of the form z maps to either plus or minus z plus a constant. So, so suddenly it's a much more rigid structure than we had before. It's a complex coordinate, so it's consistent with the complex structure on x, but it really freezes what the picture looks like if you have, you have actually a rigid picture of the complex plane, and if you choose a different coordinate chart, you only change this by translation, that's the C, or by change of sign. Okay, so that means that I can tell what the x-axis is, and I can tell what the y-axis, what the real and imaginary axes are, kind of as an object on my surface, right? So what I actually get on the surface is these coordinate charts actually produce a kind of rigid picture of two foliations and a Euclidean metric in which they are picked out to be the horizontal and vertical. Except for the finely many points, so somewhere in this picture there are these places where I have a singularity, and this should look familiar because this is the picture we drew before. It's a pair of transverse measured foliations. Okay, so that's a picture. We'll call this object, we'll call it phi, this structure on the surface. So we've added structure to x, and what am I trying? I'm trying to describe a map from x to y. So what we get is actually, we get, say, phi x on x and phi y on y, with respect to which the map is of the form, I guess, x plus iy goes to, in the x coordinate, and this is kind of in the x structure, phi x, goes to, and I guess what I want to do is I want to multiply the x coordinate by, I guess, x k to 1/2, and the y by k to -1/2. So this this is exactly a K quasi-conformal map. It's a map with K, that K equal to this constant K, because it's stretching and shrinking by the correct ratio. So this picture is in the coordinate charts of Y. I guess if I'm being careful, it's this with a plus or minus and then maybe a constant, right? I don't know, because that's exactly the ambiguity of these charts. So what it's doing, it's what we drew last time for a pseudo-analysis, but now it's happening between two arbitrary Riemann surfaces. We are taking a rectangle and mapping it to a thinner and shorter rectangle. Okay? So this map is smooth except at the singular point. So already we had to leave the smooth category to describe the map. Okay? This is called, is it clear what the definition is? So, so
Could you push the upper or the lower?
oh, sorry, this one up?
Yeah.
Yeah. Okay. All right, so that's what a Teichmüller map is. And Teichmüller's theorem says that these exist, so I'm going to take a political stance here and attribute it to bears. It's there. It says that there always, for all x and y in a Teichmüller space, there exists a unique Teichmüller map, which minimizes k, so it's exactly the correct value of k for x and y. And moreover, once you write it down, you realize something else, which is that you could actually change, you actually get a one-parameter family of maps here. You could consider, let me say this a little bit informally, consider maps of the form x plus iy goes to x, sorry, e to the t over 2, x plus I e to the minus t over 2, y, where t is between 0 and, say, log of, oh, shoot, is it log of k or half log of k? I'm gonna get in trouble with the half. Let's see. I think this is right, the way I've written it. Right? Ugh. There was a half in my definition up there, which now I'm gonna, okay, well.
I think you said that all numbers would be wrong.
Yes, I did say that.
You could be in trouble here if you actually make this correct.
Okay, so for consistency with the previous lectures, we'll keep the numbers wrong. Okay, so what have I gotten here? I've gotten a family of maps. Now what are these actually? They're not quite maps from x to y. They're maps from a local chart in x to a local chart somewhere, right? It produces a new local chart, actually. So what this is actually producing, these produce local charts for not y, but for some family, y sub t, where y sub 0, so what I'm getting, so y sub 0 is x, and y sub, whatever that number is, log k, is y. So I've produced, if I think about this kind of synthetically in the Teichmüller space, I've produced a path from x to y, a continuous path. And because of the uniqueness part of Teichmüller's theorem, every point along this path, given by this formula, is exactly at the distance from x that I think it is. It's exactly, that is the optimal map to that point. So this is a geodesic. So what we proved, what we stated, sorry, about Teichmüller space is that any two points are connected by a unique geodesic, and the geodesic has an extremely explicit form once you have the correct coordinates. So you have to know something about what kind of coordinates can occur on x. All right, but that's kind of the picture of the
There's an x missing? Plus or minus.
oh yeah, sorry, yeah, x. Right. Okay, so these things are called Teichmüller geodesics, and they have this very nice synthetic picture. You can really kind of study them. And the other thing, of course, about this is that it connects us exactly to the structure that we started with in the first lecture, namely the measured foliations, because we have from this picture, if you take the vertical lines in the plane, those are exactly the leaves of a measured foliation by the definition we used. And if you rotate the picture 90 degrees, the parallel lines of the x-axis pull back to give the other measured foliation. So we have a pair of transverse measured foliations. And in fact, so I guess it's a theorem. Which way do we want to say this? Yeah. So if I fix, well, I might as well admit I kind of wanted to avoid saying analysis words too many times. But phi, what kind of object is phi? This set of charts. You can actually think of them more or less somehow the kind of as a pointwise object on the surface. The data that gives you this is called holomorphic quadratic differential. And maybe I'll say it just so that you know how to look it up, but I won't explain if you haven't seen it before. So it's some kind of a holomorphic tensor on the surface, which is exactly equivalent to the structure I gave there. The point of saying these words is to make it plausible that this is some kind of a linear object. In fact, the space of such, so Q of x is the space of all holomorphic quadratic differentials. By the Riemann-Roch theorem, you can kind of find out what kind of vector space it is, and it is in fact just a vector space of dimension, complex dimension 3g minus 3, which is just the right dimension for us because we want the Teichmüller space to have dimension 6g minus 6, and we have that. So in fact, you can kind of, so these quadratic differentials, which are those objects, they live in a kind of nice family, and they give you directions to move in a Teichmüller space. So then the ray structure, so it turns out the ray structure, well, let's say it differently. The unit ball in this, these are all the quadratic differentials of unit size, and size in fact translates here, it turns out, to area. Area is well defined in this picture, so you can just write down the area of this structure. So if you fix the unit area quadratic differentials, that's just a sphere of the right dimension, and it is a theorem that if you take one of these things and you extract from it the vertical foliation, okay, so it's not here the theorem. So the statement is, take one of these pictures, it's just forget everything except the vertical measured foliation, and you will get, and up to scaling, you will get an element here, I guess. Actually, maybe I don't need the yeah, maybe I'll just, sorry, forget the one for a second. Take the whole thing, extract the vertical measured foliation, you will get a measured foliation. Okay, so this is that picture. So the theorem is that this is a homeomorphism. So this is a theorem of Hubbard and Maser. So somehow, so we have another way in which measured foliations appear. They appear as a way of describing the rays emanating from a point x. Okay, and there are other ways which I won't talk to you about.
Just to be really boring. So I think you can't change the log k there, right? Because the log, you have to put the log k in order to get the right thing here.
Yes?
So this is a geodesic with speed a half.
Maybe that's right. That's what I was worried about, that I was somehow letting it be speed a half.
It's
Yeah.
okay. I could erase the twos, but that's fine. Who cares?
Well,
Everywhere.
except here I wanted this to be the rotation k, except
Then I should shut up.
I can't get this right. There's no way.
Even with help.
It's not possible.
Very good.
So, okay. The coping strategy is to decide the things that are too hard to do that you don't care about. Okay. So what's so the good news is we have suddenly a nice picture. Here's the picture we now have. Here's a point in Teichmüller space, and here's Thurston's compactification by the projective measured foliation space. And then there's a nice map action by the mapping class group. which on this closed ball. And then also at X, we have a ray structure, which gives us the geodesics in this space. And it's also parameterized to, sort of the unit sphere in that sense is also identified with PMF. Right? So where am I going with this? Obviously, the right thing is that these rays should this all should fit together. So, for example, you can sort of see it's the right thing because when you apply this map, what are you doing? You are collapsing the leaves of the vertical foliation. So, in a kind of structure of this Euclidean metric on the surface with singularities, we have exactly the picture we drew in the first lecture. We're taking the vertical leaves and we're collapsing them, and so in the limit we should get the R tree back. And so this looks just like what we wanted it to look like when we described the boundary. Okay, so looks great. The bad news is it's not true. So this is like the first sign of danger at the boundary. So this is the theorem of Kirchhoff. Yeah, so I'm trying to only cite theorems by roommates. Okay, so the theorem is that, first of all, so this...
You should move.
Oh yeah.
When did you room with bears?
I was gonna say, is bears hiding somewhere?
In our apartment? I don't know, yeah.
Or even worse, Teichmüller.
Yeah, okay, I'm just adding to my list of wrong things now. Okay. So the theorem is that this doesn't work. The theorem is, so one version of it is, I guess, that MCG does not act continuously on the ray compactification. Okay, and I think that's the right way to say it. The right way to say it. So what's going on is this: if you act by the mapping class group on this picture, you will take this point to a different point, say f of x, and now there are rays emanating from this point. The rays are in correspondence with each other because they're all identified with PMF. But what happens is the rays from here and the rays from here, they don't have the right accumulation property. The rays that are supposed to have the same limit don't quite have the same limit. I'm not quite saying this right. But the point is the two compactifications are inconsistent with each other, and therefore they cannot be equal to Thurston's, because Thurston's does have continuous action. So I'm not going to get into details of this, but I just want to say that the enemy here is that in the beginning we talked about complex structures and hyperbolic structures being equivalent things, but they're not really the same thing, even though there's a correspondence. And so the geometry of what's happening here is kind of controlled by the complex structure and then the Euclidean structure of these quadratic differentials. But the behavior at Thurston's boundary is controlled by the hyperbolic structure of the surfaces. Because that was the thing that we were collapsing. We collapsed in a hyperbolic plane to get a foliation. And these things, while there's a correspondence, that kind of the geometry of it behaves badly asymptotically. And so when everything gets distorted, things grow in different ways with the different geometric pictures. And so that's not a proof of anything, but it's a reason to be suspicious. So, and in some sense, that's what's underlying the trouble. And a lot of what I want to talk about today has to do with what we can say about the structure of what's going on here. And I guess I should, okay, so the next kind of, this was in the, I guess, late 70s, but now kind of more recently, various other kind of much more detailed things have been proved about this. So another theorem of the different versions of this thing, I think, probably, let's see, so Lengen, and Maser. I'm going to put names here, but there are several versions of this theorem. Right, and then there are kind of improvements by Graffi and Madami. And Leininger, Chris, are you on this list?
We're not roommates.
Yeah. And the statement is basically, so somehow array, a Teichmüller array, can accumulate on a positive dimensional. In fact, there's more you can say. Let me just say it in this kind of weak way, subset of EMF. So this is in so if you draw the picture in Thurston's compactification, this thing goes to infinity. It has to accumulate somewhere, and the answer is that it kind of accumulates on a positive dimensional subset. What this has to do, what's going on here is that there will be some. This is going to end up being a simplex of measures on some fixed foliation. That's one way to think about it. It's a foliation which admits more than one measure, and all of those measures can be, all those measure classes can be obtained as limits of the array. So there's some kind of at least examples where this sort of behavior happens. So that's another indication of the disagreement between these two different pictures. Okay, so yeah.
So the rays do give a compactification, it's just not.
So the point is they give many compactifications. So for every base point, you get a compactification, but they're not consistent with each other. That's the problem. Whereas Thurston's compactification doesn't depend on a base point. Okay. So where else are we going with this? So well. So things are kind of intricate in here, and the focus I want to, the things I want to talk about have to do with kind of understanding the geometric structure of this space better than this picture suggests. This picture looks kind of all very uniform, and it makes you want everything to just look like hyperbolic space or something, and in fact it's quite non-uniform. So let me talk for a couple of minutes about that. So the thick-thin decomposition. The Teichmüller space is the following idea. If you it starts with the thick-thin decomposition of a surface. So suppose that X is, say, a hyperbolic surface. So what does it look like? Well, there's some uniform constant called the Margulis constant, which allows you to divide a hyperbolic surface into standard pieces, and they kind of look like this. There's sort of you look at X is a union of the thick part, which is where the conductivity radius is bigger than, I guess I don't know, let's just say epsilon naught, and where it's equal to, where it's less than epsilon naught, and this is called the thin part, and the structure of these is the following. So the thick part looks, well, the thin part first, looks like a union of collars, where the core of the collar is a geodesic, say gamma, whose length is less than epsilon naught. And in fact, let's call it, well, it's just some number less than epsilon naught. And then there's the thick parts, which are sort of, which are thick. Every point in the thick part has a ball around it of definite radius. Okay, so this kind of lives in a compact family of shapes, and these things are, they can just get thinner and thinner and thinner and longer, so the width of this thin part is roughly log of, 1 over the length, something like that. And so on, and then there's other pieces. Okay, so there's some kind of decomposition of the surface into a bounded number of thin pieces and a bounded number of thick pieces, like that. Okay, so, and it could be that there's no thin part, right? It's possible that it's all thick, and then it would just be the whole surface. So you could ask now, what does it have to do with the Teichmüller space? So now you can divide our Teichmüller space into its thick and thin part, where the thin part is the part where there is a thin part, and the thick part is the part where there is no thin part. So, that was terrible. Right, so you can write, so let me say concretely, so inside Teichmüller space, let's call it, suppose that gamma is a curve on the surface okay, then the length of gamma is a function from the Teichmüller space to real numbers, which gives the geodesic length of gamma on a given surface. And now you can ask, you can say, let T gamma, I guess epsilon naught, be the set of structures where the length of gamma is less than epsilon naught. So here gamma would correspond, on that surface gamma would correspond to such a piece of the thin part. And now you have a region in the Teichmüller space where that gamma is short. And so you get some kind of, well, we don't know what it looks like, right? So here's our Teichmüller space. And then there's a bunch of regions, T gamma epsilon, and here's another T beta epsilon. And they somehow are arranged in the Teichmüller space. So, so what do they tell us? So first of all, an important thing here is that the sort of, I'll say something more concrete in a second, but sort of a point here is that the geometry built in the Teichmüller space detects the thick-thin decomposition. So in other words, if we look, I mean, obviously, this picture I drew depended on knowing the surface, knowing what we mean by a point X. But if all I knew was that I had a space with this metric on it, I can look around and make measurements in the parameter space using this metric and decide whether or not I'm in the thin part. I claim. Okay, so these regions, they're not just kind of abstract mappings of the space which have to do with the interpretation in terms of parameters of surfaces. They are actually visible in the parameter space itself. I'll give you an example of a statement about that in a second. So we kind of want to understand how that's true. And here it's important to have not done the case of the torus. This is one reason to avoid the torus. So this is false. This is false for S equal to the torus, or the puncture torus actually, or if I allow the surface with one puncture and genus 1, it's also false for that, because in that case the Teichmüller space is H2, and H2 is completely homogeneous. So there's just because somebody came around and marked up some regions in H2 doesn't mean that they affect the geometry of H2. But that homogeneity is the outlier, and the general situation is that you can actually tell where you are in the Teichmüller space. So I want to talk about that, and I want to talk about the pattern. What is the pattern of these regions? Okay. So what is the thing to say? Let me say a couple things about them. So maybe let's look at this one first. I think. No, let's look at the first one first. Okay. So what is the geometry of one of these regions where there's a kind of thick, where there is a thin part? So suppose it may be more than one curve, in fact, that's short, right? In the same. So suppose I could have done. Let's just do it for one. Let's just do it for one. So what is? Let's think about this for a second. So, what does this region look like? Well, there's some curve that's extremely short. Let's imagine if we choose. Actually, let's think about epsilon much less than the Margulis constant. We're allowed to choose a smaller epsilon and have the same discussion if we want. And then we'll see kind of a very thin thing in another. Here's an example of what we see. Right? Let's take this example. Gamma is this curve, and then I have two pieces. Say S1 and S2. And remember that, so you could ask, if I know that gamma is extremely short, what else can happen? Well, I can deform the structure on the two pieces as much as I want, and leave this one short, and I would still be in this region. So, in fact, it turns out that this region, let me first say kind of, what happens in the limit? Suppose I let the length of gamma go to 0 over here, I could still sort of extract the limit. I could sort of see what happens in the complement. I could imagine what are called noded Riemann surfaces, or stable curves in the language of algebraic geometry, in which I still get an object, and the object will be a surface with some punctures. In fact, it will be this surface and that surface. So I kind of expect that the limiting structure is going to live inside the Teichmüller space of S1 across the Teichmüller space of S2, so that I should naturally expect there to kind of be a product structure. And moreover, you should expect, certainly you expect kind of locally, that the metric that we defined, the Teichmüller metric, remember, was defined as the supremum of something, right? So that remember that the distance from x to y was a supremum. Well, it was like, if I chose, sorry, let me be clear. If you take the supremum over the points in the surface, let's write k of f. K of f is the supremum of kf of p over p in the surface, right? That was how we defined it. So when if we pinch this off and we have two disconnected surfaces, then the supremum here and the supremum there kind of don't interact. And so we expect the metric should be is like a soup metric on this product. That's kind of what the limiting picture should be. That there should kind of become independent if we just take the soup of the two metrics. Okay. So there are various ways this is kind of an old subject, and the infinitesimal structure, you can kind of understand what the unit norm ball of the metric looks like at a point, and it does kind of degenerate towards something like this. That's, I think, known. And the theorem I want to talk about, since we're talking about coarse properties, is there's kind of a coarse theorem that says the same thing for the entire region. So here's a theorem. It says that this set can be identified with, I'll say what this means, with a product, in this case, the Teichmüller space of S1 cross the Teichmüller space S2 cross one more kind of two-dimensional parameter space, which has to do, so this parameterizes the length of gamma, length and twist parameters of gamma.
Is that term also due to a roommate?
It's due to my wife's roommate. Yeah. And the equivalence here, so what does this mean? So this here is a product of metric spaces with the soup metric. And this is in kind of an approximation of metrics up to additive error. So it's slightly better than a quasi-isometry, because the error is only additive. Even for very large distances, it's still true that it's an additive error. So that tells you a little bit, I guess, let's see, what do I want to say from this? This is one way in which we can tell where we are. Okay, the further out we are in this thin part, the more this behavior, the stronger this behavior is. And so by finding these large kind of product regions, we know that we are in the thin part. Okay,
you say the additive error is how? Depending on?
Oh, I don't know actually. So it's not, the additive error doesn't go to 0 with epsilon as far as, well, I guess I kind of think it should, but I don't know that. I'm not sure that's true, because it has to be, this is kind of true over large distances. So I don't think the additive error goes to 0. However, the deeper in there you are, the bigger of a kind of region around you has this structure. When you are near the boundary of this set, you can't make big regions all around this product structure, because they come out of the product. So
When you're near the thick part, you can't make big regions.
when I'm near the thick part, I can't do this.
Right. If you're deep in the thin part.
If you're deep in the thin part, you get big regions around you that have this kind of product structure. Yes?
You can suggest audience members that they can ask you technical questions later.
I see.
Just saying.
Just saying, okay.
Does anyone know what he's talking about?
All right, let's see, did I? Okay, so so this is what the thin part of the Teichmüller space looks like. And this is one of the reasons things are complicated, because we wanted, in this picture, we want to pretend the Teichmüller space looks like hyperbolic space. which is negatively curved, and this is very far from being negatively curved. This kind of product structure, in fact, it's almost like positive curvature because of the soup part. If it was just a L2 kind of combination of metrics, it would be like a flat geometry. This is even worse than flat because of the soup metric. So, so that's one interesting feature, that you kind of lose any hope of negative curvature by looking at these regions. And then the other side of the coin is that you can get back some negative curvature by looking at the pattern in which the regions are organized. And that's the second part of this. So, yeah, okay. So let's try to say that. So what is the pattern? So in other words, when do they intersect? So here's, let me make a claim. Here's an observation even. The observation is that this is for a suitable choice of epsilon. The following is true. That if you take a bunch of these regions, say T gamma 1 epsilon through T gamma k epsilon, this is non-empty if and only if gamma 1 through gamma k are pairwise disjoint. Okay, and the reason is this picture I drew of the collar up there. If you, I mean, it's just evident, right? If you have every short one, if gamma 1 is short and gamma 2 is short for the same geometry, they have to have disjoint collars.
So you could say for epsilon less than epsilon naught, as you introduced.
Yeah, so epsilon naught was the Margulis constant,
That works.
and that works. Does it work? I want to make sure it works because the thin parts are actually different. Yeah, I guess that works. So epsilon less than epsilon naught. Sure. I was trying to make sure that I wasn't making a mistake, but since you so as soon as there are these collars that are well defined, they can't, they are disjoint. And okay, is that clear? And the other thing to say about this, even without kind of appealing to some to that particular theorem, the shorter the core is, the longer the collar is. You know, the collar is the width of the collar is logarithmic in the reciprocal of the core length. That's just kind of that's also hyperbolic geometry, and therefore as soon as that's too wide, the other one can't cross it. That's all. So they're all disjoint. Well, so that picture shows that if this is non-empty intersection here, then they must be pairwise disjoint. And in the other direction, you have to be able to construct some hyperbolic metrics. And I will not explain this except to say French-Nielsen coordinates. So if you want to look it up. But the point is, if you have a bunch of disjoint curves, you can actually choose metrics in which their lengths are whatever you want. And so you can certainly find points in this intersection. So inside the Teichmüller space, we have now a pattern where these things, they do intersect. They do intersect, and they might intersect in kind of a pattern like this. I'm trying to draw them so that they are non-compact, by the way, because they are non-compact, because you can send the length all the way to 0, and then you go to infinity in the Teichmüller space. So these are kind of big, infinite-sized regions, and they might intersect, and when they intersect, they correspond to that pattern. So what's called the nerve of this family is just the simplicial complex whose vertices are the regions and whose simplices connect regions that intersect. So it's kind of a picture like this. If you draw a dot for every region, and then you attach an edge whenever two regions intersect, so in this case you get, I'm drawing the edges in the picture, but they're abstract edges, and then you put a simplex in whenever 3 intersect, and so on. That's the nerve, and that's a simplicial complex, which is called curve complex. C of S. So this was defined by Bill Harvey. It's kind of an analogy of Pete's buildings for homogeneous spaces. But it was for this exact purpose, kind of, or another way to say it, it's the combinatorial structure of what are called the compactification strata in the Teichmüller space. If you pinch a curve and you look at the pinched noded Riemann surfaces, then they kind of interact in exactly this way, the pattern of all the noded Riemann surfaces. So there's some complex like this, and that complex, well, various features about it. So it's so some features of this complex. First of all, it's finite dimensional. Its dimension is, I guess, one less than the number of curves you could possibly put, which is, so that's -4. So it's finite dimensional. So this is one of my numbers that's either correct or incorrect. So it's finite dimensional, but it's locally infinite. And the reason it's locally infinite is that, I mean, if you think about it a little, not so hard, if you pick one vertex in this complex, so now because of this observation, I can relate these regions to just the curves that define them, and the intersection pattern is exactly disjointness. And so if you take a gamma that's a vertex in here, then how many edges are there attached to gamma? Well, it's all of the curves that are disjoint from gamma, and there's infinitely many, because you can kind of put whatever you want to draw in this complementary surface is all going to be disjoint from gamma. So it's a locally infinite complex. And once you have it, so it's an infinite complex, it has infinitely many vertices, and it's locally infinite. So now it's not obvious what its diameter should be. Maybe it's finite diameter, but in fact it's not. So the diameter is infinite. I think this is usually attributed to Kobayashi. And somehow, so you could think of it as some kind of a metric space, which is explaining this pattern inside Teichmüller space. And the theorem that Howie and I proved in the 90s is that this complex is negatively curved. It's delta hyperbolic in the sense that I quickly mentioned yesterday. So for example, what does it mean to be delta hyperbolic? So the literal meaning is that if you draw in this complex geodesic triangles, they would be thin in the sense that I said last time. So every edge of a geodesic triangle is in the delta neighborhood of the other two edges. So that's one kind of fact. Another fact is geodesics are stable. Which is to say, Morse, I guess. The current term for it, right? If you have a geodesic in this, it's a combinatorial space now. It's a complex. So a geodesic is some sequence of edges of minimal length between the endpoints. If you have a geodesic, and then you have a quasi-geodesic, which is just an efficient path connecting the same points. So the only property of a quasi-geodesic is that it's making progress through the space at kind of a definite linear rate. It's no faster than 100 miles an hour and no slower than 2 miles an hour or something, kind of all the time. And such a thing is a bounded distance from a geodesic. So that's the stability property. This is not true in Euclidean space. It is true in hyperbolic space. So that's hyperbolicity. All right. Sort of ran out of time to say what I wanted to say. But the second part of the theorem I want to mention is the connection between this and Teichmüller geodesics. So Teichmüller, part 2 of that theorem is that Teichmüller geodesics project to quasi-geodesics in this complex. So if you're trying to study the Teichmüller geodesics that we started with, let me draw one more picture, the same picture again, repeating myself a little. So here's a Teichmüller geodesic in the Teichmüller space. And it passes through some of these regions, right? It kind of goes through, here's one, and then maybe here's another one, and so on. They're all, I'm supposed to draw them in infinite diameter. So there's some kind of a pattern in which a geodesic travels through this picture. Now actually it might come out of them entirely, because I chose my epsilon some small number, so it might be in the thick part some of the time too. But even if it's in the thick, when it's in the thick part, it's not too far from the thin part. So that's something you can check. That every point in the Teichmüller space is a bounded distance from the thin part. And so there is kind of it's a little bit rough. You don't have to, you have to, everywhere you go, you can kind of relate yourself to one of these thin regions, but maybe there's a choice. Maybe here you could choose either one. Maybe here you could choose, more than one. Over here or something. So it gives you a kind of a rough path through the curve complex, and that rough path is a quasi-geodesic. And that might sound sort of bad because who knows what that might be, but at least this statement about stability of geodesics tells you that you're actually close to a geodesic, an honest geodesic. So a Teichmüller geodesic and a curve complex geodesic are related in this way. Let me add one more word to this. These are unparametrized, which means, so a geodesic is something that travels at definite speed, not too fast, not too slow. That's not quite right here, because maybe the geodesic will spend a very long time in one of these balls, one of these things. And then, even though it spends 1,000 years, even though the Teichmüller distance of this segment is very, very long, in the curve complex it's sitting in one place. So maybe the speed of this path is not actually constant, and it's not kind of a definite speed, but maybe it actually gets stuck for a long time. But it kind of travels through this picture monotonically. So if you just reparameterize the time variable here, then you would get an honest quasi-geodesic. So that's part of the statement.
So you never have them stay for longer and longer in the thick part? That's never a problem?
They can also stay longer and longer in the thick part too.
And,
But they would have to keep switching off what are the short curves that they're close to.
I
So
suppose you still
that
get
can
this
certainly
geodesic,
happen.
But you
So-
still get this quasi.
Yeah, then you get, when you're in the thick part, then you're traveling at a definite speed in the curve complex. Then the speed at which, then you don't have to worry about this extra adjective. Maybe as an example, I forgot to say this before, but when I was talking about Teichmüller geodesics, the kind of important class of Teichmüller geodesics are the axes of pseudo-Nosovs. If you take a pseudo-Nosov element, remember we drew this picture. We drew a picture which looked just like a Teichmüller geodesic, right? We had this, pseudo-Nosov had a pair of foliations, and the map just kind of did exactly what we wanted it to do when we talked about the Teichmüller geodesic. And in fact, so then a pseudo-Nosov defines a one-parameter family of surfaces along which it's just acting by translation. It's exactly moving you by a Teichmüller map. So a pseudo-Nosov will have an axis which is a geodesic, and that axis will sort of travel through this, and because of the periodicity, this axis will have a symmetry of it. The pseudo-Nosov is acting by translation on the axis. Then by some kind of compactness argument, it never spends too long in the thin part. And so these guys actually travel at definite speed, so speed bounded below, through the complex. Okay, so
And
yeah.
question, because at the opposite of pseudo-Nosov, you have geodesics that just shrink curves and you are not seeing several cells, no? If you just shrink a curve?
If I shrink one curve,
Yes.
then it's not a pseudo-Nosov.
No, get rid of the pseudo-Nosov, but you have Teichmüller geodesic that just...
I could do that, yeah, I could, for example, so I could take a surface and I could choose, I could foliate it by curves that are parallel to one particular curve, right? This is what you have in mind. And then I could shrink this.
And you are always in the same t gamma epsilon in that case.
That's right, in that case, right, so
Your
that
critical
geodesic
point.
will kind of land like this in one.
Yes.
Right, so that produces a quasi-geodesic which is very slow, right? So it just kind of stops after a while.
It's not the point, the projection?
Well,
Eventually.
eventually it's a point, but maybe, if you follow it in backward time, this gets longer and longer, and then you do other things. So you could, for example, if you want to complete this picture, choose two curves. Choose this curve and some other curve that's much, much longer, transverse to it, right, but closed. And then in forward time, this one, say, let's call this one alpha and this one beta. In forward time, alpha shrinks, and you go to the region associated to alpha. The backward time, you go to the region associated to gamma, to beta. And
It's
these
finite
could be
time.
very far apart. In between these two regions, there could be all sorts of stuff happening. Kind of more or less anything. So,
It's finite geodesic.
so this will be, this is a finite, it's an infinite geodesic in the type of
Projects to
space.
finite.
Curve.
Projects to a finite geodesic, quasi-geodesic in the curve complex.
Okay.
But the length of that quasi-geodesic is, could be anything.
Uh-huh.
Okay. That's a good question. So I'm supposed to have a break, right?
Maybe